Everyone. Hi. Hello. Welcome to the ACOM seminar. It's my pleasure to introduce today's speaker, Dr. Doug Worsnop. Dr. Worsnop received his PhD in chemistry from Harvard University. He was a Humboldt Fellow in physics at the University of Freiburg, Germany, and he joined Aerodyne research in 1985. He also has been a Finland Distinguished Professor of Physics at the University of Helsinki since 2007. Dr. Worsnop is a fellow of AAAS, AGU, and AAAR, and has won numerous awards. He has over 600 publications in chemical kinetics and aerosol chemistry. In today's seminar, he will talk about atmospheric aerosol chemistry, climate, and air quality. Doc, the floor is yours.
Thank you. It is a pleasure to be here. I will be here a total of 5 days, and I won't stop talking the whole time. The purpose of this slide is to say that, as you just heard, I've been at Aerodyne Research for almost 40 years. And then 17 years ago, I started a part-time professorship, but long-term professorship at the University of Helsinki. I'm also affiliated at other universities in Finland. And then in more or less the same time period, I'm now actively collaborating with all those groups up there in China. And the real point of this slide is that everything I'm going to say today was done by all of these people and many more. I don't really do any work anymore. So this is going to be a summary of the results we've gotten in the last 25 years applying mass spectrometry to measuring the atmosphere. And I say we're going from 1 nanometer to 1 micron. The 1 micron is the aerosol mass spectrometer that measures the chemical composition of sub-micron aerosol, PM2.5 aerosol. And the 1 nanometer is chemical ionization mass spectrometry, where we measured a bunch of new molecules in the ambient atmosphere. And what excites me the most, we measured a bunch of molecular clusters, which are the key components of the chemistry of nucleation of new particles in the atmosphere. So I'm going to, this talk is more or less a highlight slide, a collection of highlight slides from my career. But I have a purpose. So, I should also mention that CERN, that one of the key things when I went to Helsinki, after I went to Helsinki, I got involved in the cloud experiment at CERN. And I'll have a fair amount to say about what we have done there. So, I like to introduce aerosols in the atmosphere with this slide. This is one of the first field campaigns we took the aerosol mass spectrometer to in Pittsburgh as part of the Pittsburgh Air Quality Study in 2001. And you have two pictures here on a clean day and a polluted day. A key number here is that, that you should always realize. This picture that is taken from 10 kilometers. That skyline is 10 kilometers away from the camera. And the key point about this is this polluted day, 40 PM2.5, 45 microgram per cubic meter, was a clean day by EPA regulations then. The EPA daily standard for PM2.5 then was 65 microgram per cubic meter. It's actually true that soon after this picture was taken, they reduced the daily standard from 65 to 35 microgram per cubic meter, where it still is today. And the point is, nobody would believe this was a clean day. Now, the other part of this is that on days like that in Pittsburgh, often when you look at it from a satellite, this haze is actually continental in the eastern United States. And in fact, often, the weather pattern was set up so that you advect that aerosol, that haze, to Europe. In those years, I mean, the Europeans spent a lot of time trying to measure how much we were the problem in their air. And now, in the western United States, we do the same thing with China. But the key point is, days like this in Pittsburgh or the eastern United States just don't happen anymore. They just don't happen. The Clean Air Act has worked. I mean, as you all know, the only counterexample to that is when Canadian forest fires impacted eastern U.S. Now, what's important here too is that haze over that dark ocean is the aerosol direct effect. That's by far the strongest aerosol direct effect. Obviously, when you have that haze over the dark ocean, let alone if it makes more clouds, you're reflecting more radiation than any other aerosol situation. But the point is, that doesn't happen anymore because we've cleaned up the air. In the same time period, Asia has compensated for us because their haze got much worse, and there were pictures like this of the outflow from China going over the Pacific Ocean. But the point is, they're cleaning up their air too. Nobody wants to breathe that stuff or look at it. And my small comment is this is why aerosols matter. Because this is going to increase global warming, depending on who you talk to, by 0.5 degree or 1.5 degrees by the end of this century, if we continue to reduce the aerosols. So, with that introduction, at Aerodyne, my group at Aerodyne, we built this mass spectrometer. There are now roughly 400 of them around the world. And this is, for me, a really simple device. I'm going to go through this quickly. We have an aerodynamic lens that magically takes in particles at atmospheric pressure. In low pressure, focus them into a beam that we inject into a differentially pumped mass spectrometer. The other key point is our detector. It's a really simple tungsten oven heated at 600 degrees C. And now we use a time of flight mass spectrometer. I put up this guy, Y.T. Lee, here because he's one of the guys that taught me everything I know. I inherited his instrument, which was a complex molecular beam mass spectrometer. And he and my supervisor back then, W. Hirschbach, won the Nobel Prize for this. But all we have done is adapt the same vacuum principles, low pressure principles, and pump away all the air while getting, only 1 in 10 to the 7th air molecules reaches the detector, while all the sub-micron aerosol particles do. So we're concentrating the particles by up to a factor of 10 to the 7th. I want to go through this quickly. The particles just hit a vaporizer at 600 degrees C. That vaporizer is placed at the center of an electron impact ionizer. We ionize everything that comes off that vaporizer in the gas phase and then measure it as positive ions. The beauty of this is a universal quantitative detector. Everything that comes off that oven, we detect. What we miss in the atmosphere are refractory materials, or dust, or elemental black carbon. But all what we call the non-refractory components, we detect all of them, and it's quantitative. It's not hard to calibrate. There are still issues, so our definition is non-refractory aerosol, which is whatever vaporizes is 600 C. This is a raw mass spectrum. We've subtracted out the residual air, And all this shows, I'm not going to go through this, is that we can resolve inorganics and organics pretty easily from the fragmentation patterns. And then the green that's left is all the organics. Realizing that we're detecting everything, but we are fragmenting, decomposing, and fragmenting most of the molecules. So there's almost no parent molecules here. And the only comment I'll make about this is I think there are roughly 1,000 people in the world who know these colors and these MOVs by heart. And this is another one of my really favorite slides. What I haven't mentioned is that when we accelerate the particles into the vacuum chamber, they have a size-dependent velocity. The smaller the particles, the faster they are moving. The larger ones are moving slower. So when we measure the time of flight of the particles, we can get a crude measure of what we call the vacuum aerodynamic diameter. And these are almost the two first size distributions among the first that were ever measured. This is the Manchester group, James Allen and Rami Alfara. In 2001, they went to Jeju Island in Korea. And then in 2000, they had been in Edinburgh, Scotland, next to a street canyon. And these size distributions in these colors here, the chemicals, summarize everything the AMS has ever measured. Not quite everything, but what's most general. In Jeju Island is one mode at about a half a micron diameter. That's the accumulation mode. And if you go into the city, there's another mode at about 100 nanometers. And it's important to know this is vacuum aerodynamic diameter. But the same accumulation mode. And that's the traffic mode. That's the accumulation mode. The traffic mode is actually, these are fractal soot particles of dimension 1.9. And in the vacuum aerodynamic space, they'll appear at 100 nanometers. And what we're measuring here mostly is the lubricating oil that came from the diesel engines that produce these particles. In Jeju Island, you see we have sulfate, what appears to be mostly an internal mixture of sulfate, organic, and nitrate at this half 500 nanometer diameter. This is typical of the remote atmosphere. They all look the same. The relative ratios of the different colors depend on what's upwind. I would love to go back to China now, and I should have mentioned, this was designed, and this is outflow from China, long-range transport. If you do in fact, it's been done. If you do it now, the blue is the largest and the red is the smallest, because they have China has reduced 80% of the SO2, just like we did in the 90s and 2000s. And here we see the same thing. And the important thing you can't see in this slide is that the green on the right and the green here are not the same. They're different organics. And our method of choice for deconvolving that is what we call positive matrix factorization, where we take our time series of complex mass spectra and quantitatively deconvolve them into different source factors. And this is the first example of that, or one of the first examples, where we have three mass spectral factors, and what's important here is they look very different. I mean, the PMF is resolved very different chemistries. One we know. Well, I'm going to skip over this. The first one is heavily oxidized secondary organic. This one's medium oxidized secondary organic. And this is HOA, hydrocarbon-like organic, that comes from a diesel vehicle. And in fact, what's on here in red is the mass spectrum we measured chasing a bus in New York City. And it's identical. So we have resolved in the city this HOA, and then we have the secondary components that either the what we now call LVOA tracks sulfate very well. HOA tracks black carbon, CO, and this one, in this case, tracked a tracer that was measured by the Goldstein group that clearly came from biogenic VOCs. So we've now been doing this all over the world. I'll go through this quickly. During this time, we shifted. This data is with a quadrupole mass spectrometer with a unit mass resolution. We've now shifted to time of flight, the key point being that the black here is the resolution of a quadrupole here, and this is the resolution of the time of flight mass spectrometers, and you can see at this particular peak there were actually 5 species that under the right conditions we can resolve. And now these are the typical factors we get for secondary organic, primary organic, and then biomass burning. And before I get to this, I forgot to say one key thing here. My point here is this: if you're worried about climate, this is mostly the only aerosol you care about. The only time you ever see this is when you're in a city, especially if you're next to a street or a highway. This is super important because we happen to live there and we breathe it. If you're worried about health effects of aerosol, you worry about this. If you're worried about climate, you worry about that. And I'm going to say to a high approximation that every experiment, every site, everywhere we've gone, it's mostly the same story. So let me go through this. So we get to this. This is get to this slide, which is the paper that Jose Jimenez and Manjula Kanaratna et al. We published this in 2009, where this is the summary of 40 field campaigns from 17 institutes using the AMS as of 2007, 2008. I used to say this was all over the world. And at some point I realized it's only all over the Northern Hemisphere, because at that point we had not been in the Southern Hemisphere. Now, I'm not even going to try to explain these pie charts, except to say what it shows is that worldwide the aerosol chemistry is roughly half inorganic and half organic. When we published this, that wasn't news. That was already well known. But we were able to measure the organic continuously in real time, with much more resolution than anyone had before. And most important is the average O to C, oxygen to carbon ratio, in all this organic aerosol worldwide. The average ratio was 0.7, is 0.7. And that was a big revelation. All the chamber experiments, they truly were smog chamber experiments then. The average O to C was more like 0.2 or 0.3. And this is true everywhere. And the real virtue of the AMS that I'm going to keep talking about is that on that 600-degree oven, we volatilize all the carbon, except for black carbon. And even black carbon we can now do with a laser, if we had a laser to it. But we volatilize all that carbon, especially the highly oxidized carbon. It actually is the bulk of the carbon that ends up in the aerosol. And we uniquely, it's what we call M/Z44. It's symbolized by CO2+. That's just a decomposition product of highly oxidized organic, which is the carbon on average that gets into the aerosol particles. So I like to say at this point that the cleanest site on this diagram was Hutila, the Central Forest Station in Finland, where we've done a lot of work, and Beijing, where it was 80 microgram per cubic meter. In the meantime, Beijing got and this is actually, I should say this, PM1, not PM 2.5. PM 2.5 in Beijing is roughly twice this high. In the meantime, that was measured in 2005. In the meantime, Beijing went up to several hundred microgram per cubic meter, but it's now back down to less than this now. And that was a haze event. But what's interesting here is this was the cleanest place in the world, and that was the dirtiest place in the world. And since this was published, almost all my work was in those two places. And then finally, this legend, which is the details of the O to C ratio, is sitting on top of India. And the reason it's sitting on top of India is there were no AMS measurements in India when we published this. Now India, unambiguously, Delhi, gets the record for the dirtiest air in the world. And now they have a bunch of AMS, well, they're beginning to be more AMSs there. This is another one of my favorite pictures. This is a campaign in Mexico City in 2005. Where we took our Aerodyne mobile laboratory and drove it on top of this hill, this mountain, overlooking Mexico City. Mexico City is unique in its meteorology that in the morning you can have really clean air, both really clean in ozone and in organic aerosol. And then during the day, on top of that mountain, we just would watch the haze come up to us. And this is what the OOA, oxidized organic aerosol, and OX, O3 plus NO2, plot one versus the other, and they just go up together during the day. You don't see this anywhere else in the world, because nowhere else, almost nowhere else, do you start out this clean in the morning and get this dirty, up to 200 ppb of ozone in one day. And this was the best direct evidence that this oxidized organic aerosol, secondary organic aerosol, is being made by the same photochemical processes that make ozone. Again, this is a place I'd love to go back to because they have, it's much cleaner now than it was then. So to summarize everything I've said, the big issue when we started is how much of the aerosol is primary from combustion and how much of it's secondary from gas phase oxidation of vapors. And the answer is it's much more secondary than primary. Even in Pittsburgh, unless you're right next to the trucks, there's twice as much secondary as primary, normally. And without going through, I mean, the rest of my talk is all the stuff I covered up here. But the idea is the same processes that are making ozone are making a few highly oxidized, low volatility molecules that condense into the aerosol. So in the AMS, we were able to measure both sulfate and organic. The difference is that sulfuric acid is more or less one compound. If I put NOx here going to nitric acid is more or less one compound going into the aerosol. And we also measured the organic, which is thousands of compounds. There are hundreds or thousands of these, or thousands or really 10,000s of molecules in the organic that it condenses. And what the AMS does is just simplify all of these things into hydrocarbon, lightly oxidized, highly oxidized, levoglucosan, isoprene, and so on. But we're not actually factors, but we're not actually measuring any molecules. To summarize this again, this is the life cycle of an aerosol particle, published by Alona Rippinen et al. In 2010 or something, 2009. And what this is showing is we have a whole bunch of molecules These are supposed to represent low volatility molecules that might condense and stick to one another to make a cluster, molecular cluster, which then can grow into a nanoparticle and then grow larger to become a 100 nanometer particle or a CCN that can nucleate cloud droplets. And the key here is that, so if everything I talked about with the AMS said that the CCN-sized particles are composed of oxidized organic, secondary organic, and sulfate. If you're near an urban region, you're going to get a lot of ammonium nitrate too. And that's what the AMS measured. Now, it was exactly at this point in my career that I accepted the position in Helsinki. And in the aerosol community, it's well known that in Helsinki there's only one process in the whole world that matters. And that's the formation of these clusters and nanoparticles that initiate nucleation and new particle formation. And I was literally hired to measure this. But there's a really important point about this diagram, this life cycle, in that we were trying to measure these low volatility species that under the right conditions can condense on molecular clusters and initiate nanoparticle growth and eventually CCN formation. The very important aerosol microphysical fact is that actually 99.9% of these low volatility molecules condense on these particles. They condense on the condensation sink. They very rarely, the conditions have to be perfect, starting with the condensation sink is low, it's clean, and you've got just the right number of these molecules to outcompete the condensation on the bulk aerosol, which means when you study these molecules, you're actually also studying a large fraction of this, because we're actually measuring the molecules, all of which condense on aerosol. So, when I went to Helsinki, it took us 2 years to invent this thing, configure this thing we call an epitaph. All this epitaph does is sample ions from the ambient air directly into a time-of-flight mass spectrometer. This was done by McConnell and Hague Union, and all this stuff you see on here is just all the stuff in the lab we used to try to characterize how well it worked. But actually, all I'm going to talk about is we go to the, we just take this instrument in the ambient air and we measure ambient atmospheric ions. I'm going to come back to this, but my hero, my guru in this context was a guy named Fred Isley, who developed all this. Everything I'm going to talk about for the rest of the talk is us just copying Fred Isley. The big difference is that we replaced his quadrupole mass spectrometer with what we call a high-resolution time-of-flight mass spectrometer. It's not really high resolution, but it's higher resolution. And this is just true. So, the very first day and night that we took this instrument to Huhtala in the boreal forest, this is what we saw. This is literally true. During the day, we saw sulfuric acid clusters appear. We even saw a sulfuric acid cluster with ammonia in it. And the appearance of these clusters correlated exactly with the appearance of nanoparticles in all the particle counters. It's just amazing how good it is. And this is more or less what we expected to see. but it's sulfuric acid with ammonia. But at night, we saw a completely different spectrum. I mean, the smallest point is at night, there's no sulfuric acid production, so sulfuric acid goes away, and it turns out that nitric acid is the most likely species to accept electrons in the ambient air. I should note that this is all based on either cosmic rays or radon decay producing ambient ions that are ubiquitous in the atmosphere, around 1,000 to 2,000 per cubic centimeter. So we saw this. Now it took us about a year, and then we immediately saw these big peaks, big signals at these big masses. What's important is this is the gas phase. These molecules are in the gas phase, and they're now obviously colored green, which in our parlance means we think they're organic. It took us about a year to figure out, this was my favorite molecule for a while, that at 340, this peak was C10H14O12 N- in the gas phase. It took us another year to figure out that it's really C10H14O9 clustered with a nitrate anion. And the question is, how can you have C10H14O9 in the gas phase? What's obviously immediately apparent is the main VOC, 80 or 90% of the VOC in here is alpha pinene, a terpene, which has a formula of C10H16. It sure looks like we managed to add 9 oxygens to alpha pinene while only losing 2 hydrogens. Exactly at the same time, this is just true, literally a month after this spectrum was measured, we had the first planning meeting for the cloud project at CERN, which is a 26 cubic meter, ultra clean, polished stainless steel chamber at atmospheric pressure that can be temperature controlled between minus 50 C to plus 30 C. It's super clean. The gas control systems, I'm going to say, are the best in the world for simulating the remote clean atmosphere. And now we routinely place 6, 8, or even 10 of time of flight mass spectrometers around this chamber. Now, in 2009, when we had this planning meeting, all I realized is, and this chamber just happens to be next to the original positron-synchrotron, 1961 positron-synchrotron at CERN, which is the seed for all the other synchrotrons, including this big circle, which is the Large Hadron Collider. The important thing is to use the LHC, they have to turn this positive synchrotron on. And we have the lowest energy beam available at CERN, and nobody else wants it. So we permanently have access. We have this chamber right next to this pion beam, which is almost a direct simulation of cosmic rays. What I understood was that when you turn that beam on into this chamber, it would be the best atmospheric pressure chemical ionization source ever built. And we had this mass spectrometer that could sample the ions that accumulated in that chamber. And this is what we saw. Immediately, you put SO2 and ammonia into the chamber and turn on the lights. You see a nucleation event, the appearance and growth of nanoparticles, and we see sulfuric acid ammonia clusters. You do the same thing with dimethylamine. We see dimethylamine sulfuric acid clusters. You put in pinene diol as a surrogate for alpha pinene. You put, with SO2, you turn on the lights, and you see sulfuric acid with bands, which these are C10 molecules clustered with sulfuric acid, C20, C30, C40. And then I compare that to the boreal forest, Hutula. Well, this is what we see. The difference here is all these spectra were measured with the beam on. And this is why it's the best chemical ionization, atmospheric pressure chemical ionization source ever. So that, okay, where am I going now? Oh, yes. So going back to, yes. Now looking at this one, I've got those labeled as band 1 through band 4, where this is it's very similar to this band 1 and band 2. The beautiful thing about the CERN experiment is that we can actually time resolve the appearance of all these clusters. For me, as a physical chemist, going back to my PhD, everything I've done, this is my favorite slide. Because we're taking these bands of sulfuric acid, C10, C20, so on, clusters, and we're resolving it. And the point is, the appearance of the largest clusters takes a half an hour. And in this experiment, we have measured the collision time of the molecules. I mean, we don't know exactly what it means. We're really close, because the sticking probability of these molecules to each other is really high under these conditions. And again, as an experimental physical chemist, this is just beautiful. So I come back to this, and what was important here is that we understood that this was, when we understood this was a nitrate anion cluster, we realized we could detect these things as neutrals if we made a nitrate CIMS. And again, at the same time, Tuukka Pataja had been a postdoc here with Fred Isley and Jim Smith and Lee Malden, and they built a copy of the Isley mass spectrometer with a quadrupole and took it back to Helsinki. It arrived in Helsinki actually the summer after I arrived. And that was a nitrate quadrupole CIMS. What that meant, though, is once we understood that we were using nitrate anions to detect the organics, we realized all we had to do was to put the Isley source in front of the TOF. And via Tuukka Pataja and Lee Malden, back then, that was an NCAR collaboration. That I was not involved. I was involved in this, but not in the original. And as I like to say, the rest is history. So the first slide I like to show is this is I don't admit this. I think this was in Helsinki, but on a strong nucleation day, we measured sulfuric acid clusters with what now we call the CI or epitoph. And what's important here, so we have sulfuric acid monomer, dimer, trimer, tetramer. The lesson here is in the ambient air, if you want to measure sulfuric acid clusters, you need to have high resolution. I don't believe that before this there was any ambient observation in anything like normal conditions that resolve the trimer or the tetramer. Because what you see here is all these organic signals. The organic signals, the same signals we first saw in Hutula, are everywhere in this spectrum. So that this is, and I can say this, Fred knew in his nitrate CIMS, quadrupole CIMS, that there were signals at every m over z. But they were tiny, and there was no way he'd ever figure out what they were. And all we have done is replicate what Fred did, but with higher resolution, and depending how you define it, up to 1,000 times more sensitivity, only because we collect all the ions all the time. Anyway, and this is another moment to tell another one of my favorite stories. I mean, there's this guy in the back of the room, when they were flying the DC-8 300 meters over the ocean, they kept seeing this signal that when they looked at it, wasn't at the right mass. It's the same mass as N2O5, but you look at it carefully, it was just not the same mass. You can see the mass resolution by comparing this one and this one. So they were different. And this is motivated by the fact that there's no way there's any N2O5 300 meters over the ocean. And to make a long story short, they discovered HPMTF, whatever that is. It's a 50%, it's the, above 0 degrees C, 50% of DMS, or some number like that, actually gets oxidized through this molecule, eventually to SO2 and sulfuric acid. And anyway, I believe in high-resolution mass spectrometry. Now going back to Huhtala, that nighttime spectrum. Mikhail N., after finishing his PhD in Helsinki, went to Jülich to work with Thomas Mentel in what they then called the plant chamber. All they did, their plant chamber, is mix ozone and alpha-pinene. And lo and behold, this is essentially the identical spectrum that we measured in Huhtala. It's actually, it's different because they're using isotopically labeled nitrate, but anyway, it's the same molecule. So we're seeing C10H16O9, C10H14O11, C20H32O11. And the question is, where do they come from? And so that this is what we then called ELVOC, extreme low volatility organic, C10 and C20 molecules in the gas phase with an oxygen and carbon ratio that can get up to 1. And it immediately became clear that these things can participate in nucleation and nanoparticle, cluster formation and nanoparticle growth. We now prefer to call these HOMs. Our nomenclature is really lousy, but highly oxidized molecular organics. And now there's a cottage industry measuring, compounds with different precursors under these conditions. The key to this is autooxidation, which had been discovered before. It was discovered originally in aqueous chemistry by German chemists in the 1870s. But it turns out in the atmosphere, under relatively clean conditions, it's ideal for this. I don't really want to explain this in detail. The bottom line is we can add 3 or 4 or 5 oxygen molecules to in this case, the terpene backbone in seconds. It's autooxidation. You form an alkyl radical. You immediately form a peroxy radical in a 20% oxygen atmosphere. That peroxy radical can then abstract another hydrogen nearby, and you have a cycle. And there are definitely people in this room who understand this chemistry better than I do. The most important detail here is the fate of these peroxy radicals depends on how much NO you have, how much ROX you have, how much ROX you have, how much HOX you have. And this is now a cottage industry. I think we've invigorated peroxy radical chemistry because you can chase these patterns all over the world, all over the lab. And in fact, just before this talk, Ching and I were talking, and she pointed out to me that RO2, I mean, this is dumb. RO2 NOx-HOX ratios in the lab are super important, and this is what we do now. We can use these as markers of how well we're simulating the atmosphere. Now we have this nitrate CIMS that can detect all these molecules. So what do we want to do? If you're working with me, you want to do PMF. Positive matrix factorization of the nitrate spectrum. This is work that Xiao Yan did during his PhD. And so we take the nitrate CIMS spectrum and do PMF, and we get 7 factors. And these factors are amazing. I mean, there's 2 nighttime factors. One of the nighttime factors disappears during the day, the other one just gets lower, and then we have all these daytime factors. And what's important is, without trying to explain it all, these are the mass spectra of these different figures. And we have these in high resolution. You can't see that here. And my point is, they're all different. And it turns out, this is the anidol, the original Hutala factor, nighttime, and these factors, daytime factors, all have are dominated to varying degrees by organonitrates. Because the point is, in Hutala, the NO goes to 0 at night and then has this cycle. And you see one of these factors has almost the exact same shape as NO. One of them looks a little bit sulfuric acid. One looks more like sunlight than the sulfuric acid does. We're just looking at a complex, in this case, auto-oxidation of alpha-pinene, and we get this complex mixture. And the other key point here is the NO was roughly 50 ppt. Most people think this is low NOx condition. But that amount of NO, going back to the auto-oxidation pathways, was enough to completely shift the chemistry from pure highly oxidized organic to organonitrates. And for us, as new particle formation people, this is really important, because organonitrates are more volatile than non-nitrate HOMs. So we have those spectra. So I come back to this one. I mean, and now I'm looking at Hutala. This is what we did in cloud. The question here is, which one of these is cloud and which one is Hutala? In order to get this, it took us 5 years to do this. We had to have the right mixture of alpha-pinene, delta-chlorine, SO2, ozone, light to make OH, and then we had to tune the ammonia and the NO. And this is my dream if you're in the lab, to simulate these things. And if I go back to this one, you see the complexity of this. This is how many molecules we detect. And this is the cloud one. We see bigger ammonia clusters, and we see more organic because the signals are better. But my point is that mess is the sum of all of these. We were mimicking the daytime condition, so it's the sum of all these mass spectra. And that's how complex this really is. And this, for me, this is the power of PMF, is to separate that into different components. So we simulated Hutala. And that leads me to this paper by Joost de Gouw, who I think most of you know. I mean, this is his perspective in AGU perspectives on Earth and space scientists. It's his career. He talks about the AMS a little bit and PTR. He has this figure which we made together 20 years ago. First time we tried to compare gas phase and AMS data. But most important for me, in section 2 in his paper, the research described here wouldn't have been possible without developments in mass spectrometry. And then the most important one, Doug Worsnop likes to call this the molecular revolution in atmospheric chemistry, and I have been fortunate to be part of it. This is really important. I have a peer-reviewed reference to Doug Worsnop and the molecular revolution in atmospheric chemistry, because this is what I believe. And so my vision is we use all the bloody mass spectrometers we have simultaneously. We measure all these molecules, we do PMF, we do lab studies, and we figure out what's really going on. And to put this, yes, and then this is the schematic at the end of INAR. This is the figure that as it was published. This is a schematic of going from 1 nanometer. This represents forming the molecular clusters and growing them to 100 nanometers to form CCN. And the idea is in the current atmosphere, most of the nucleation, most places, is some combination of sulfuric acid and a base. And then, but the growth to 10, 20, 50 nanometers is dominated by organics. I mean, to the extent we're still reducing SO2, anthropogenic SO2, all we're doing is shifting this a little bit more towards organics. Now, this is what was published, and my main contribution to this figure was to make these font sizes legible. Because Michael Hand just thought VOC was the king. This is what we think now. There is some VOC, extreme low volatility. This can condense on nanoparticles. There's a ton, much more LVOC, low volatility organic, that can detect on ultrafine particles, condense on ultrafine particles. And it turns out NOx is super important to understand the distribution. There is some ULVOC, ultra volatility organic, which can actually form clusters all on its own, and we have just detected them in Finland. But and then if you go to China, it looks like this. There's just a ton of stuff that can grow the particles to a micron, whatever. Where am I going with this? And then we call all of this organic in here HOM or OM. We're really highly oxidized organic matter, oxidized organic matter. We're really precise with our terminology. Anyway, and my point is we can now detect all of this, and then going back to this diagram, we've now detected, but it wasn't a coincidence, these were colored red and green. It turns out most of the smallest clusters are more red, but as soon as you get to here, to 10 nanometers, it's all organic. So that what's important, there are two important things here. First of all, we have found this highly oxidized organic that is often formed by autooxidation, and to a large extent, every organic molecule, even isoprene, but every anthropogenic, to some degree, undergoes autooxidation. For yields, what I haven't mentioned is the yield for these HOMs in low NOx conditions for alpha-pinene is about 5%. And if you do limonene, it's closer to 10%. The anthropogenic organics are 1, 2, or 3%. But we are also measuring what's over here, about half of what actually ends up in the larger particles in remote, non-polluted conditions. So that this is what the AMS saw, and this is what we measured with the CIMS and the epitaph, where we think most of the time in the current atmosphere. You need sulfuric acid and a base, but the organics, low volatility organics, dominate the growth. And what I'm saying is the growth and the accumulation of mass in the accumulation mode and new particle formation is the key to understanding how the aerosol life cycle in the atmosphere. And then the statement is this is like 5% of the organic on average ends up as compounds low enough volatility to go into the aerosol. But if you make a CCN nucleus, that impact on climate is much larger than any molecules quite like it. What's important here is this is controlled by sub-PPT concentrations. The PPT concentrations that grow eventually to larger concentrations. What's important, again, as an aerosol scientist, is 1 PPT of condensable vapor over 24 hours makes a ppb of aerosol. So these concentrations just accumulate into the aerosol. Now, if you're in China and it's really polluted, this can shift from ppb going to ppm. But PPT concentrations matter. And this is my sales slide. You need an epitoph and a CIMS and an AMS to do this. And then I'm not going to go through this at all, but this is where, across the world, where we have observed nucleation in the ambient atmosphere. Essentially, every process we measured in cloud or vice versa has been measured in the atmosphere or in cloud. And then I'm going to stop here. My last message, this is only to aerosol people, but to everyone. I mean, particle number and particle mass matter. There are a lot of people, I mean, if you work for the EPA, the only thing that matters is particle mass because PM 2.5 is regulated. If you're in Helsinki, the only thing that matters is particle number and how many CCN there are. But they're equally important and completely different measurement. Mass is relatively easier to measure. The number, aerosol number, is tightly coupled to the size distribution. It really matters whether it's a 5 nanometer, 50 nanometer, or 500 nanometer particle. And that's hard to constrict all this. But what I'm saying is that even though the yield of these organics is only a few percent, they have, for example, oxidized organics, they have a huge impact on the nucleation process that's necessary. And ultimately, one needs sufficient mass if you're going to grow the particles large enough to be CCN. And that's my message and how to measure that. And I'll stop here.
Thank you, Doug, for an exciting talk. For people following online, please type your question underneath the video box, and we can start the question in the room.
Doug, thank you for your inspiring talk. So, your last sentence there, climate simulation needs both. So what do we need to do to get to anything that could work for that?
I mean, the fundamental problem from a climate modeling standpoint is that nucleation, new particle formation, and cloud and CCN and cloud formation are inherently, this is my opinion, are inherently sub-grid scale processes that are not linear in any way. And if it's true that aerosols and clouds are the largest uncertainty in our climate simulations, I mean, I didn't say much about clouds. I mean, a cloud for me is what can happen after the particle grows to 50 or 100 nanometers. And even though the cloud people love the cloud microphysics people say the chemistry of those particles doesn't matter once they're big enough, which is largely true. In order to that get big enough, you need chemistry. And until you get the budget of even the nucleation process and the growth process right, you're not going to get the CCN number right, I mean, in a future climate. I mean, look, Ken Carslaw has a really famous paper where he says that 50% of the CCN are anthropogenic. No, 50% come from new particle formation, and 50% are anthropogenic, for primary emission. We in Helsinki are sure that's not correct. It's more like 20 or 25% or 75%. 25% from primary emission, 75% from nucleation. And I mean, and we don't have, nobody has good numbers on that because the nucleation is really spotty. I mean, and it only happens, nucleation normally happens at 10 a.m., between 10 a.m. and 12. Because that's when the sun comes up, you start oxidizing everything, and then you start growing stuff, and you turn the nucleation off because you're increasing the condensation sink. And this is just true. But if the CCN number, in all the simple models, if you increase the CCN number, you get brighter, you get smaller cloud droplets that make brighter clouds that are more long-lived. And if that's true, we don't know what the budget of the particles was 150 years ago, and we don't know what it'll be in 2070 or whatever, 2050, when we keep reducing the SO2. I'm involved in studies in the Antarctic, the Arctic, and the Antarctic. DMS, okay, this is important. DMS and its oxidation, if you fly over or the air flows over a penguin colony, you get unbelievable nucleation. But you need a penguin colony. But that nucleation doesn't make very many CCN, at least on the time scales we can measure, because there are no organics there, or very low organics. And in terms of our changing atmosphere, we're going to change the ratios of a lot of the precursors, and that could change the CCN budget by a factor of 2. We don't know. But all I'm claiming is as long as the IPCC keeps saying that the error bar on the uncertainty of the climate warming is dominated by aerosols, and they say that the largest error bar within that they ascribe to SO2, or sulfuric acid, we are perturbing the SO2 systematically. And we're going to go back to DMS being more, the idea is pre-industrial DMS and volcanoes. Volcanoes are not zero here. Are the largest source of sulfur, and sulfur in our atmosphere, as we understand it, is still the most important species for making new particles. That's not the only species. I didn't mention iodic acid here at all. Iodic acid is even better than sulfuric acid, but iodic acid is not ubiquitous. But in the Arctic, iodic acid may be as important as sulfuric acid, but that's another story. Anyway, that's my statement.
Thank you. We have a question online from Jim Roberts. What is your perspective on how we can connect all this molecular detail to what other people want to know? Health effects, aerosol indirect effect, oxidative formation.
My perspective is buy a mass spectrometer, work really hard, and figure it out. But these molecules are what are really there. And these molecules are also ones we breathe. mean, this is how complex atmospheric chemistry really is. And if I want to be positive, we have over the years, I mean, we have now developed these mass spectrometers so we can measure, I believe, most everything that is important. I glossed over a ton of details because I interchange CIMS spectra and Apitas spectra, and it's actually really complicated. But that's what's there. And the most important thing is 99% of these molecules as individual molecules don't matter. We don't have to chase every single one, chemically and otherwise. But collectively, they are what's going on. I hope that answered your question, Jim.
Okay, more question in the room? Yes, Elma.
So yeah, thank you for this really nice summary of everything that has been done in the past years. So I had just a question. So if you cannot afford the full, instrumental CIMS and the AMS, and only can have, like I said, these mini AMSs, ACSMs, could you maybe comment on what do we lose in terms of potential for discovery, because we cannot see and resolve everything? So what is but we have them for a long time, so how do you see that play a big role in discovery?
The main virtue of the ASCENT network in that context is measuring all the time, getting the seasonal variation and the long-term variation, and long-term trends. And in the context of what I talked about, then you figure out what intensives to do to better resolve the chemistry. But the long-term measurements, if we can do it well enough, and as we were talking, this is where long-term calibrations really matter and all that. But the idea is to measure the trends, the relative ratios of sulfate, nitrate, and organic. And what's also true that I didn't talk about at all is biomass burning. If biomass burning keeps increasing, it may dominate, it may become as important as anything I said today. And an ACSM measures that really well. It gives you a quantitative measure of what the impact of biomass burning is. But I am explicitly saying it's hard. And and how this eventually gets translated into models, where if you introduce one species or whatever extra species, the computer people get upset, but the computers are getting faster. Anyway, I'm the detailed measurement guy.
It's already 12:10, and I want to thank everyone for attending, and Doug will be here till Friday, am I right?
Yeah, so I'm here all this afternoon.
Okay, yeah, so you can still
and I will, and I can come back here tomorrow afternoon if anybody wants to talk.
Okay. And yeah, that concludes today's seminar, and we'll see you in 2 weeks. Thank you.
Okay.